section on multivariable calculus. Looks like it's exactly what's needed. So, div, grad, curl, and all those integral theorems, that's what we're going to work out today. We had a really good start in the recitation in the previous lecture. So, let's see how to, we want to do integral theorems. But yeah, this is just the whole world of multivariable calculus. And what I'm going to also steer towards is the multivariable Taylor expansion. It's going to be really useful. Since we started the whole semester off with single variable, this is going to be good. Eventually we're going to get into linear algebra and we'll have a lot of good tools for it. So far, we had for the derivatives, we had gradient of f. And so f is a scalar, the gradient is a vector. I'll just go ahead and write our definitions out. df dx, I hat, df dy j hat, df dz k hat. We have the divergence, which turns a vector into a scalar. So you've got a vector field f. The divergence is the sum over these derivatives, fx with respect to x, fy with respect to y, fz with respect to z. Okay, so here you're turning a scalar into a vector, here you're turning a vector into a scalar. Okay. And then we had the curl of the vector, turns a vector into a vector, and we're just going to write this formula here. It uses the cross product out of the determinant well-known formula. So this is just formal, but it does make the point that this combination of derivatives itself is a vector operator, right? Because the cross product of two vectors, and here you're treating the derivatives as vector operators. So then you get what you get here, okay? So we had those, we had some good examples going on. The example that's on the homework, we have V, I'll write the general one down, omega cross R over R to the N. Over R to the N like this. So this is just a vector field. If you put the right dimensions in here, then you'll have velocity, but otherwise the vector field. This omega was, I'll write it this way, 0, 0, omega as that vector. And what we had was the R x squared plus y squared. We reduced it to a two-dimensional vector for that homework problem. But this is kind of a generalized rotating bucket that we're going to do some more work with. Okay, so we have this so far, and we did this in the recitation yesterday. Get a really interesting result when you do the curl of this vector. Okay. And the picture that goes with this is the rotating bucket. So you've got something here. What you learn, you've got this rotating thing. What you learn is that the curl is like your rotational type of vector. Good, so we did all that, and we're still working on that. And then we had integration. And this is what we want to continue pursuing, is the integral formulas. So the integration we had so far was our most basic integral formula. So this predates the vector business, f of b minus f of a. But then we saw that, and I demonstrated, proved it, that if we have a line integral from one point to another in space, and f is a vector, actually, and we have the gradient f of r along a curve, so dotted into dr, then that is equal to f of, I'll just write b f of a, positions there. Now, I didn't say that much about this type of vector here because the proof is pretty elementary. This is a line integral of the type, you know, a vector along a curve. I'll call the curve gamma of r. Dotted into, because that's what we have here, dotted into this element here. And this type of line integral in general, you have to have a parametrization, or you have a parametrization f of r tau dr d tau. That would be your dot product, and you'd be integrating over this parameter tau from tau sub a to tau sub b. This is very similar to what we did with the length of a curve. But yeah, that's what we're looking at. This is what we're looking at in compact form. The line integral. And what we want to do is go up a dimension and then another dimension. The thing about these integrals is they replace the integral over a derivative by an integral at a boundary, or by something at a boundary. We're going to see in a moment the next iteration of this. Okay, so what we're doing now is integral theorems. So I'm going to go ahead and erase this. We're going to keep up here for a moment. So for vector calculus, you can say this is the first of the integral theorems, the line integral. Okay. So integral theorems. And the next one would be the following. You have, so this time the derivative that we're talking about is the curl of a vector. And that curl of a vector is dotted into a surface normal, and we're going to integrate over an area. So in keeping with this theme here, the integral over derivative, something over the endpoints. What are the endpoints of an area? Here's the, you know, your textbooks always draw some kind of potato chip, whatever, okay. That's the surface, right? And the surface has an oriented curve on it, and everywhere on the surface there's a surface normal on it. Okay, so there's an oriented curve, surface normal, and so the boundary, the endpoints of this surface are the actual boundary. That's the way to look at that. And so I'm going to use this symbolism here. That is the boundary. We're looking at a closed line integral, and we're just looking at f dot dr. So that's the integral theorem of Stokes. And the reason it's, and I'm going to be more explicit about it, it's like this fundamental theorem here, because here's the derivative, and instead of the endpoints, we're talking about the, you know, the integral on the boundary there. Okay. The curl of f dot n hat dA, and this can be thought of as a flux. Okay. So this here is a flux through a surface this is the integral along the boundary here. So I'm using boundary of A for that orient curve and there's an area. Good, so we can do an interesting example. And I'm actually going to just set it up and do it for the homework. You know, setting up surfaces can be pretty difficult or time or labor intensive. But we want to do a very simple surface. What we want to do is the rotating bucket problem here. Okay? So we want to evaluate this theorem with this rotating bucket field. Guess I do have to erase it, but we know what we have up here. Okay. So the example, and I'm just going to put this up as a homework problem and just get started on it. So we want to do or evaluate Stokes' theorem. That capital S, Stokes. The rotating bucket problem. So how do we do that? Okay. We already know that got this rotating bucket here. You can think of this as X, Y, and Z, right? Bucket rotating, and there's a vector field associated with it. And that vector field that's associated with it, remember, was just these velocity vectors. That's the thing rotating around. And the curl of this was the vector that was pointing straight up. So the curl of B was this one right here. So what we're going to do is let A be a circle of radius R. Circle of radius R that's centered on the origin in the XY plane. So if we do a top view, you know, that's our circle of radius R, that's the top view. Then we take the curl of F, which some of us already generated yesterday. So we take the curl of F, and what's n hat going to be? This one we just systematically take to n hat is going to be the unit vector k, right? And since the curl was also in the k hat direction, that's going to take care of itself, okay? So this side of the integral, it's got a radial dependence, except the curl is a constant for n was equal to 0 on it. You guys remember that? Yeah, the curl's constant, n equals 0. So yeah, you're going to just be doing a basic symmetric surface integral out from 0 to r of that curl, which should be no problem for any of those values of n. Okay, 0 to r, integrate this side. So yeah, the left-hand side, just go ahead. So we've got circle of radius r. Okay, that's the area there. We've got the curl of that vector field B. The n hat is just k hat, and since the curl is itself in the direction k hat, that just takes care of that. And then you've got d area. And since you're going to have the circular symmetry, you'll probably be able to do the 2 by r dr d area type of situation. You guys familiar with that? D area could be 2 pi r dr. Because when you've got a circle, So that's what we're looking at. We're going to have a pretty basic integral. When the curl of v is constant, it's 2 omega in that simplest case, right? When the curl of v is constant, you're going to have that constant value times what? Pi r squared. Because that'll be the area of that circle. So you definitely have some easy limiting cases going on. So that's the left-hand side. What about the right-hand side? Now we have to have the vector dot dr. But remember, the vector is a tangent. So on the top view here, the vector is tangent everywhere. So the integral v, make some room over here. The integral v dot dr, that's also going to take care of itself. The dot product is, because these vectors are always tangent to the dr itself, and the dr is going around in a circle. So note that n equals 0 case, we're going to get 2 omega times pi radius squared for that integral. And over on this side, we're going to get omega r times 2 pi r. So this is the simplest limiting case. So again, the 2 omega, if you've done that calculation, that's the curl of our vector field when n is equal to 0, right? And then pi r squared, you know, that vector's pointing up, pi r squared is just the area integral, the area itself, so I just multiply it. Now on this side, omega r is the magnitude of that vector, and n is equal to 0, and 2 pi r is just integrating around that circle. And lo and behold, they equal each other. So that's the simplest version of Stokes' theorem here. Now the general case of n, you're going to actually have to calculate that and do an integral on both sides. Okay. But it shouldn't be hard. Now there's going to be an interesting case, because when n is equal to 2, we found that the curl vanishes. Okay. So the curl of that vanished when n is equal to 2. But, so the left side is going to vanish, but the right side is not going to vanish. And that puts us into a really interesting conundrum. Who's wrong? Okay. So there's a value of n, we just calculated it yesterday in the presentation, where that curl vanishes. But this right side integral around here is still going to have something finite. Okay. Anybody point out what's going on there? It's a really interesting case that we're just led to organically. How can that be? How can both of these, you know, how can Stokes' theorem still be true? If you have something finite on one side and the curl of it is 0 on the other. This is the first time we're naturally running into the idea of a delta function. Because that curl vanishes everywhere, but it's not defined at the origin. So there's an infinity at the origin that integrated up gives us exactly what's on the right side. Okay, so you're going to run ahead. Who's heard of the delta function? I know some of you guys. Has anybody heard of the Dirac delta function before? Yeah. Some of you have, some haven't. But this is a place where it just comes in naturally out of the vector calculus itself. Okay, didn't have to be brought in an ad hoc way. So I'm just going to put that as a note, because you guys are going to enjoy doing that calculation. Like I said, this is the n equals 0 case, right? So this one you can knock out. The n not equal to 0, you'll be able to do this area integral like this. because your vector field and your k hat are going to be parallel, going to take care of each other. And then you have to think about how you're doing this, but they're always tangential. Okay, so there aren't any special dot products going on there. Okay, so eliminate. Okay, so this is the first part of it. And the second part. Note that curl of B equals 0 when n equals 2 of that expression I just erased earlier. Curl of B is undefined at r equals 0 for this case. So the integral over that undefined point is what gives you a finite result on the right side. Okay? So the left side of Stokes, integral over undefined d area is what gives you this integral b dot dr, whatever it is. Okay, so that actually defines that undefined point in the curl. Okay. We're going to see that again in a couple of different situations, but here it just arose completely naturally. And I also mentioned yesterday in recitation, that vector field that we're just talking about is the same as the B field of an infinite wire, an infinite thin wire. Okay, so this stuff ties together really nicely. As far as this integral theorem goes, I can attempt a little rudimentary proof of it, which isn't bad either. So let's try that too. So this homework problem will give you a very interesting problem to work on. For the second part, you just want to write it out carefully and see what see what it's meaning. Okay, because the integral itself theorem is still true. Okay? That's a 0, but it's not a 0 everywhere. Okay, let me erase this. So what we want to do now is just look at the meaning of Stokes' theorem just in terms of these quantities here. So the way I'm going to do that is we'll just look in the xy plane, and we'll just look at literally a square. So this is x. Y. And these arrows that I just drew, they are the integration. If this were the area that we're looking at, they're the integral on the right side. So what we need is the curl of f dot n hat. And since for this thing, so here n hat is equal to k hat. Coming out of the board, what we're looking at is the z component of the curl of f. Okay, so we're going to have integral curl of f z component dot k hat dA is going to be integral of f dot dr around that square. This is something reminiscent of what we did when we were doing Cauchy's integral there. Okay. So what do we have for the z component here? We had dx fy minus d dy fx. that would be our area integral. And what would be our line integral over here? We would have, these 4 lines, so we could have fx delta x fx of x delta x plus fy of y delta y minus fx y delta x minus fy of 0 delta y. Something along those lines. Let's see if we can pull this together. This one, fx of 0 delta x y. We may have to do them on the y delta x y. Something along these lines, maybe on the midpoints. And these derivatives here are fy minus fy of 0 delta x delta y minus x. So you get 4, you get fy of y delta y minus fy of 0 delta y minus fx of y delta x. Yeah. Okay, so that's the quick and dirty demonstration of Stokes's theorem. You can be a little more careful with these, but actually we just knocked it out. So the point is that the left side here, that was the area integral over the curl. I just did the z component of the curl because that's my projection there. The right side was these 4 branches of the line integral. Okay. So yeah, you can do this really carefully, by the way. And so this was just for one square, and you can say it's an infinitesimal square, and all is well for the infinitesimal. Now suppose you have a larger area, okay, and you make a little grid like this. And what I just did was I showed the Stokes's theorem for one of these squares. Anybody remember the argument we had for Cauchy's integral theorem? What was that? You add up all the little squares, but any 2 squares on the adjacent side, the adjacent one cancels. And so eventually all the adjacent sides cancel and you just got the outer boundaries. Okay? So this actually, you guys should take this home and play around with this. Okay? I just did the definition of the curl. So that represents that integral, line integral right there. And so you can see it goes back to the literal definitions of the derivatives, okay, in the integrals. So it's useful in that regard. So that's your rudimentary proof of Stokes's theorem, just done on a single little square. You guys extend the construction. You know, I just checked them off here. This was that z component of the curl. Delta x, delta y was the area, right? So that was the integral. And here they were the line integrals, you know, the field times the delta x as we went around that square. You're gonna see we can do something similar for Gauss. But yeah, this is reminiscent of the Cauchy theorem that we had done as well. A little less rigorous, but adequate. Now, okay, so mathematicians are pulling on their ear, right? They're not liking this at all. But suppose now you have a smooth, a smooth manifold, smooth surface. Then you have to argue, if I get close enough to that, I can make it arbitrarily flat section of it because it's smooth. And then this is just an arbitrary section of some smooth surface that I got close enough to and reoriented till I had a flat plane, and as it goes up. So that's legitimate, and then it's, if you have surfaces with cusps, okay, then all bets are off, right? We don't have those here. This is for an idea of a smooth surface. Okay, I'm gonna stand by this. Good, so that's the integral theorem of Stokes, and reduced to the basic calculus definitions. And the next one is Gauss. And that's the one that started us on this, because when I was deriving the heat equation, I had to make use of the Gauss's integral theorem. So let's give this one a try. So Gauss's integral theorem, so this is Stokes. This other one, the divergence theorem, Gauss. Again, if you start with your derivative, so you've got the divergence of a vector field, and it's integrated over a volume. So we take a vector, turn it into a scalar, integrate it over a volume. So that's the derivative. Therefore, the endpoints of that volume, or the boundary of the volume, is the surface that bounds it. So now we have the flux integral f dot n hat, the area over the boundary of that volume. This one's a little trickier. We also have a good example to work with this. Maybe I'll talk about the example and then the proof. Okay. Good. Who remembers this? Divergence theorem. Some do, some don't. Okay. Very important. When you guys take ENM, you're going to see this all the time. Good. But in keeping with our theme of fundamental theorem of calculus, here's the derivative, and these are the endpoints, right? This is the boundary of the thing. You've got the volume. And so this is a closed integral, by the way. Call it that. Closed integral. And let's do an example. And what we're going to do is the divergence of a gradient. That was also in our derivation of the heat equation. The divergence of a gradient of a scalar, because that's the divergence of a vector. So that's question mark. Here we're going to use some index notation instead. Divergence of the gradient. So first of all, we're going to have gradient f is df x I. X of I half. I can do it that way. So that's sum equals I equals 1 to 3. And those are that's the ith unit vector I, j, k hat. So then the divergence of this r is equal to root x1 squared plus x2 squared plus x3 squared. And we did some of this yesterday. So it's a good one to calculate because we have to do the gradient and then the divergence. So I can get rid of. So here we have d over dx of I of 1 over r. That's the one we want to get first. So what we have is minus 1 over r squared d dx of I of the magnitude r. And let's just run through this. We did this yesterday, but not everybody. D dx of I of x1 squared, x3 squared. That's what that r is, right? So that's 1/2. This thing to the minus 1/2, and then whichever one is the ith index there, 2x of I. So that's x of I over r. So here's what we have. Equals minus 1 over r squared x of I divided by r. So that's the first part of that expression here. Now we need sum over I equals 1 to n d dxi of this thing here, of this minus xi over r cubed. Okay, that'll give us the second derivatives. I equals 1 to 3. Okay. So here we go. We've got summation, minus sign out. The first one gives us a 1 over r cubed. Okay. Minus signs out front. And the second part of the product rule here, we're going to have plus x of I. We've got a negative 3 power, so we're going to have minus 3 r to the 4th. And then we again have the chain rule that we just did right here. So we're going to get another x of I divided by r. So yeah, I'm going to keep the minus sign out front. And I'm going to have sum over 1 over r cubed, 1, 3, minus 3 xi squared over r to the 5th. Now when I sum this from 1 to 3 and I have no subscript, I have 3 over r squared. Okay. I can pull the 3 out the front here, minus 3 sum over xi squared over r to the 5th. Oh, cube, sorry. Got a cube right here. Cube. And this sum over xi squared is going to be r squared itself. So we're going to have r squared over r to the 5th minus 3 over r cubed minus 3 over r cubed. Looks like we ran into some similar thing that we did before. So this div grad here is equal to 0 for r not equal to 0. And we're going to have the same, a very analogous thing. This leads us naturally to a delta function without having to artificially define the delta function. This is naturally right into one. So what we found was, so del squared 1 over r So I have this here, so I can erase what we have here. Integral v del squared 1 over r v volume. What do we have here for the flux integral? Let's make this a sphere of radius r, just to be concrete. But what do we have for the flux integral? So f was the gradient of 1 over r, which was this thing right here. So this was the minus 1 over r squared vector r over r. And the n hat for the unit sphere the area. And this is a sphere of radius r, right? Sphere r. So what do we get on the right side here? Anybody? These are two unit vectors. They're pointing radially outward. Dot product just gives us a 1. Okay. It's being evaluated on the surface of that sphere here, which is at radius r. So we'll keep the minus sign. We've got 1 over r squared d area 4 pi r squared. Make sense? Because just remember, this is a flux integral evaluated on the surface of a sphere of radius r. And these two dotted themselves, just a 1. That's the area of the sphere. We're on the sphere, and this 1 over r squared is always the same thing. Radius r. So what's left? Minus 4 pi. So again, this thing here, which is 0 everywhere except at the origin, it's undefined at the origin, but it's integral over the entire volume, arbitrary volume centered on origin, is equal to minus 4 pi. So when I introduce Dirac's delta function in a short time, we'll actually have these two examples that came straight out of the integral theorems. And this gets used a lot. You guys have done Gauss's law in electricity and magnetism possibly at some point, and you were actually using this stuff without necessarily knowing it. Okay. So that's a nice application of Gauss's integral theorem that takes us a little beyond. What about the proof of this? What about the rudimentary proof of this? This one is a little hairier. Okay. So yeah, hold on to this. This is a good exercise to have in mind. This, again, I'm just going to say equals 0 except at the origin. But what comes out is a minus 4 pi. And sometimes you absorb the minus sign into here because it's, minus 1 over r, but that makes no difference. Okay, I'm going to erase this and keep this guy up here and then try to discuss the meaning of this integral theorem. See if we can pull that off. Okay. So here we want to talk about Gauss's integral theorem for a cube. So what's the best way to draw this cube? I'm gonna regret this. But x, y, z, we've got the origin and the cube goes out to plus x, plus y and plus z, like that. Origin's at the back corner there. So this divergence of f integrated over the volume of this cube, that's d fx dx plus d fy dy df dz, and then the volume is delta x delta y delta z. Now, the f dot n is going to be fx of x delta x of x delta y delta z, and then the other two that goes. So that would be one face minus fx of 0 delta y delta z, and then you have the other four faces as well. So that's a front face and a back face, and so that one would be from there. Okay, so if I just do this red one as a condenser, that would be those. This would be fx of x minus fx of 0 delta x delta x delta y delta z, and let's see if we have that. We have fx of x delta y delta z, these cancel, minus fx of, yeah, that actually goes that fast. Can't believe that. Math professors are pulling out their hair. So what I just did was I did 1/3 of the volume integral. I can do the same thing for fy, fz here, and those other four faces. So this is the front face, the back face, and you do it for the other two, and that's the meaning of this Gauss's integral theorem. So you do all three of these, I just did one, then you've got the whole thing over the entire cube. The divergence integrated over the cube. You see when I canceled the delta x, I was just left with these two. And this was the surface integral, I'll just write here, surface integral over two faces, and you have, two more expressions like this, and you got the whole thing. Okay, I rest my case. So that's the meaning of Gauss's integral theorem. And again, if you had a larger volume, so you've got some big volume now, and you put a coordinate system in it, and you got a whole bunch of these little cubes, the adjacent faces, these expressions on the adjacent faces cancel each other out until you're just doing the entire cube on the one hand and the surface on the other. And once again, Cauchy's integral theorem had the same philosophy as this. Good, so those are our integral theorems. And I can now return to that derivation we had done, having filled this in here. Should come up with an assignment for this, but let's think about that. derivation of the heat equation. Which I gotta find my notes somewhere. Okay, so this is Gauss's integral theorem. Okay, so let's see if I can do this up. Locate that mystery material. Where do we go? Oh, we'll pick up with that later. Here's where we're gonna go. Here we go. Okay, yeah, so to get to the heat equation again. Yeah, here we'll just put this up again, kind of to complete the circle, right, the heat equation, which is what started this whole thing going. So, if you recall, heat equation derivation. So we had specific heat. This is in your notes, actually. I just want to make sure so we started with this. We had Q MC delta T. We're making contact with physics 4B, and then the equation of heat conduction was dQ dt. I just did the magnitude at the time. A over delta L. And in my picture, that was, temperature difference. This was a temperature difference over a thickness delta L and a surface area A. Okay. So that's what we had, heat equation. You've had this in physics 4B. And we turn this into a differential equation. We let Q vector equal minus K gradient of T. That comes from the heat equation. We had here, so we had Q dot n hat through a closed surface, which was the boundary of the volume. That was equal to the minus the change of the energy inside the volume, minus d over dt. And the energy inside was going to be the density of specific heat, T, d volume. Now this one is related to this equation here, that M is the density times the volume, okay? M is the density times the volume. Energy is leaving, and so the change in temperature comes from the derivative out here in front, okay? So this is the expression that we use the integral theorems on. So this was on the volume, and this was the boundary of the volume. So this is where we would use Gauss's theorem, okay? So then we would say Q dot n hat the area, this is where we use the divergence theorem, is equal to, that's the left side here, the divergence of Q, the volume of the volume. So this is Gauss's integral theorem. Because Q is minus K gradient of T, that's where we're going to get the divergence of the gradient. Okay. So which are the two that we're comparing now? So now we can compare this. I'll be explicit about this. Gradient of Q over a volume. And it's equal to this integral here. We'll bring this one under the integrand as well now. We'll leave it outside. dV. So here's the direct comparison. Minus d over dt, rho ct, volume. Do I bring the t inside? Yeah, I'll bring the time derivative inside. The temperature is the one that's changing. So we've got minus integral rho c d temperature with respect to t. So that's the transformation that took place here, Gauss's law. And from here on out, we were just able to equate these two integrands with the minus sign inside, equate them, I'll put them all under one integral, and then bring this thing into play, because we have the gradient, the divergence of Q. So divergence of Q is equal to minus K divergence gradient of T, and this divergence gradient, as we just saw, is the del squared of T. So putting those all together, that's where we That's how we ended up with dt is equal to alpha del squared t. So now at least we have all those steps. If you go back to your original notes, you'll see we did that. We did that, and I just pulled the Gaussian argument out of the hat, but now we've got a little more background on it. So here's what we're going to do. This is a good place to stop. We want to do two things. We want to solve this equation using some of our complex techniques. And the other thing we want to do, now that we've started talking about multivariable calculus, is the multivariable Taylor expansion. Okay, those are two important ingredients, and at that point we have to start doing linear algebra, because we're already heading into the end of the semester, amazingly enough. So that's the plan. So what we'll do on Thursday is solve this. I added a couple of problems to the assignment. We don't have that much, but that's okay. Yeah. And actually, just having derived this, we may go straight to